Can you connect my laptop, please? Thank you, baby.
All right, I think that'll be good. Okay, sorry, it's not cute right now. So somebody was just asking me a question, and I addressed it, but then I forgot what the question was. Did I answer it? Daniela, was that you? Oh, about the quizzes. Right, cool.
No, yeah, about the quizzes, but you answered, you said you eliminated one, right?
Yeah, so the quiz that we would be taking next week is no longer. Right? So
okay,
that,
perfect. Will you have a practice one on Canvas? Since it's longer, or do we just keep practicing the ones that you have up there?
For the Lewis, you guys have the lab and the homework, so I'm hopeful that that will be enough for you guys. I kind of don't want to overwhelm you anymore, but we'll talk. I think we talked about in some of the videos last week that, not last week, week before. God, it's been a long week. That the types of questions that I can ask you on a quiz or an exam with respect to Lewis structures are not going to be like draw this entire structure, right? That's just not a thing that is easy for me to ask you guys to do, and it's also a thing that's really easy to cheat with. So the kinds of questions that I'm going to be asking on a quiz or an exam are going to be things like how many total valence electrons does this structure have, right? How many electrons are used in bonding? Are there any double bonds or lone pairs that are missing from this structure? Is there a formal charge on this molecule? If so, which atom is it on, right? That kind of thing. So they're more in the details, but if you don't know how to do the structure, then if you don't know the procedure for doing the structures, then you'll have a hard time answering those questions, right? But a lot of the times I'm giving you a structure and I'm just asking you to evaluate these pieces of the structure, right? Or I can give you an incorrect structure and say, hey, what's wrong with this structure, right? That kind of thing. Does that make sense? So in terms of the types of questions, it's going to be different than what you're seeing in the homework. But if you've done the homework and the lab and you're practicing with that stuff, then hopefully you should be comfortable answering those kinds of questions. Does that kind of help you guys a little bit?
Yes, thank you.
Cool. I'll see if I have a practice quiz from last semester, but I doubt it's going to be similar types of questions. Does that make sense? Just because of the format going to online, the type of question that I can ask is just different in this environment. So, okay. So, this is the beautiful periodic table that I posted for you guys. So for the octet rule, right? You've got the guys that can't follow in orange, hydrogen, beryllium, and boron, right? You've got these four guys, which are basically the only ones that follow the octet rule, which is why it's the stupidest rule that exists. I probably shouldn't say that on the record, but it's like the most breakable rule that we have in chemistry, right? So who follows the octet rule? Basically just carbon, nitrogen, and oxygen, right? So they're maxed out at 8 electrons, okay? Now, for the guys that can exceed the octet rule, right, the octet rule becomes a minimum, right? So that's the minimum number of electrons that it can have. So you can have 8 electrons around you as a minimum, or up to 12 as a maximum, right? And that's for anybody in row 3 and below that's a non-metal, right? So that would be silicon, phosphorus, sulfur, chlorine, arsenic, selenium, bromine, and iodine, right?
Sorry, to clarify, they can have 8 to 12 electrons?
Correct.
Okay.
Yes. So, any of these guys, when they're your central atom, as it were, right, they can have, usually it comes in the form of extra double bonds, right, where you wouldn't normally be able to have double bonds. So, the chlorate ion is an example of that, right? I think that one's in your homework. So you'll see these guys along the way. Sulfur trioxide, I think, is another example that you see in the homework. So these do come up. So by all means, guys, I'm less concerned with you being able to memorize this than being able to understand why like hydrogen, beryllium, and boron are not able to have a full octet. Mainly hydrogen, really. But yeah, so if this is something that you struggle remembering, just write it down at the top of your test. I mean, not physically on your test, but like on your scratch paper, you know what I mean? Like that's fine. So I don't want this to be something that you guys get hung up on. It's just a series of rules. There are actual legitimate reasons why these rules exist, but we don't really get to the depth of that information in this class. So, questions about the octet rule? The laziest rule there ever was. Cool. All right, so let's talk geometry. So, geometry, aka molecular shapes. We are literally just looking at the three-dimensional structure of molecules. Right? So I think the easiest way to look at this is for us to just go through and do the table together. This is the same table that's in your lab. I believe it's also in your lecture packet. I have to double check on that. That would be the 4.2, 4.3, something like that. But yeah, so let's just go through it and do it together, and then we can give some examples of each one so you guys can see what we're talking about with these, okay? So the simplest type of molecule that we can have has two total attachments. Oh, hey, that's my ex-husband. Okay, so two total attachments, two TA, okay? I'm just doing some definitions first so that you guys can follow along with all of my abbreviations in my table. We have two different kinds of attachments, okay? So we can either have attached atoms, oops, sorry. AA, or we can have lone pairs. LP. Okay? So whenever we're talking about geometry, we usually are referring to the, quote, central atom in the molecule. Now, most of the molecules that we've been drawing in the homework have one central atom, right? But if you look ahead to the lab for this coming week, the next week, there's some large organic molecules that you guys are going to be looking at where the idea of a central atom kind of falls apart because you have so many atoms stuck together, right? This is really common in organic molecules where you have these big organic structures, and talking about a central atom really just means whatever atom you're focused in on, right? what is the geometry around that atom? Does that make sense? Kind of, sort of? So we'll use simple examples here, but there will be some kind of extrapolation that you guys need to do when getting into these bigger molecules, okay? So when we're talking about the geometry, we're talking about the geometry of the central atom, okay? So, the simplest kind of molecule that we can have would have 2 total attachments. And that molecule would look like this. So here I have an example where I have 2 atoms attached to each other, right? Is there really a central atom involved in this shape?
No.
No, not really, right? Because there's only 2 atoms, so talking about the central atom doesn't really make sense, right? But this is the language that you guys will see, so I just want to make sure that you guys are comfortable with that, right? So if I have 2 atoms attached, there's only one type of geometry that I can have for this. And that's linear, okay? Basically, the only shape you can make with 2 atoms connected together is a line, right? Hence the name, linear. Everybody all right with that? Cool. There's one other example where I can talk about having something like this, right? Where now I have a central atom, right? That would be this guy.
Oh, sounds good.
And I have 2 attached atoms, right? This is also linear.
That doesn't make sense to me. How do you have 2 atoms?
Let's look at some examples. So this is oxygen. Oxygen is a diatomic molecule, right? It's just 2 atoms connected together. The only way that that can be arranged 3-dimensionally is in a line. Coolsies? Let's look at an example of this guy. So here I have 3 atoms attached together. Who's my central atom here?
Carbon?
Carbon, right? So carbon's my central atom, so that's the atom whose geometry we're talking about. Does that make sense? Yeah? And you can see that hydrogen and nitrogen are aligned next to it, right? But there's no way that this could be any other shape but a line, right? There's only 2 things attached, no lone pairs. That's linear, okay? You guys picking up what I'm laying down? Cool. So anytime you have a central atom that only has 2 attached atoms and no lone pairs, you're linear, okay? When we start getting into lone pairs, that's when things get a little bit tricksy, okay? Questions about that?
This is so much better than the posted videos.
Cool. Yeah, like I said, this was something that we had gone through in lecture already. So I didn't realize until everybody was like, oh my God, what is happening in these lectures? That I was like, I'm so sorry, you guys. So, and then it just happened to fall on the week that I was like, sorry guys, I'm not going to be here for 3 days. Basically, worst teacher ever. I'm so sorry, you guys. I love you. Thank you for being patient with me as I sent out my teacher evaluation forms today. I'm like, please, I love you. Okay, so is everybody comfortable with the linear geometry? It's pretty straightforward, right? Okay.
I think Jesse had a question in the chat.
Oh, sorry. Yeah, so that's kind of a weird one, right? So you don't really talk about how many attached atoms there are because there's only 2 atoms, right? So you're looking at the molecular structure, but the molecule only has 2 atoms, so the structure can only be linear, right? Because that's the only shape you can make when you're just connecting a line between 2 things, right? So, but yeah, good questions. All right. Is it okay if I erase here? Yeah? Cool. All right. So now let's get into 3. Whoops. Total attachments. So, for 3 total attachments, we have the first possibility is that we have 3 attached atoms, right? Meaning no lone pairs. So, what this looks like. Now, we didn't talk about in the first one linear, the angles that are formed there, right? But what were the angles on the linear molecule?
180 degrees.
180 degrees. So all of the atoms in a linear molecule are going to be 180 degrees apart, right? Why are they 180 degrees apart? Why not 90?
The linear?
Repulsion.
Somebody said it. I think, was that William? Was that you?
Yeah, the repulsion between the electrons.
Yeah, there's repulsion between the electrons, right? So all of the connections that we're talking about in a covalent molecule, we got to remember those connections are made by sharing electrons, right? And electrons do not like to be next to each other. So the farther apart those electron groups can be, the happier the molecule will be, right? AKA, the more energetically favorable the molecule's shape will be, right? So that's why when we're drawing these structures, right, we're always trying to maximize the distance between the attached atoms and or the lone pairs, right? Does that make sense? So in this case, right, is this a 3-dimensional molecule or a 2-dimensional molecule?
2-dimensional.
2-dimensional, right? This is a flat molecule. Does everybody see that? So, let me think about how I can do this on, right, this is where my drawing skills get really, really bad. But you guys can see that all of the atoms here lie in a 2-dimensional plane, right? None of them are sticking up out. None of them are going back into the board, right? Which would make them 3-dimensional. Does that make sense?
Is this just talking about, is this talking about how they actually are in real life, or is this just like a way of classifying?
So if you'll remember back to 100 years ago, we talked about what makes the best Lewis structure, right? We said the best Lewis structure is always going to be one that is the lowest energy. And it doesn't necessarily mean that this is the truest representation, but it's usually the most probable. Does that make sense? So basically, you can have a molecule that's arranged in infinity different ways, right? And at any given moment in time, because these things are all whizzing around and moving constantly, they probably are going to be arranged in slightly different shapes, right? But we're saying that this is the most common shape associated with 3 attached atoms. Does that make sense?
That makes sense. I'm just having trouble understanding how it can be 2D because I thought the electrons like orbited in like, you know, spheres.
I got you. Okay, so what I'm saying is the shapes are 2-dimensional, not the actual molecules. Sorry, that is a little confusing. Yeah. Great question. Thank you, Jessie.
Thank you.
Cool. So that was the confusion about this 2-dimensionality, right? Okay, cool. Yeah, so I'm literally just talking about the shapes that are being made, not the actual molecule. Sorry, that is confusing. I never thought about that. You guys are helping me learn too. So whenever you have 3 attached atoms, the geometry is called trigonal planar. Okay, trigonal planar. An example of a trigonal planar molecule would be acetone. You guys don't need to know the name for this guy. There are a lot of molecules that we'll draw in the Lewis structures chapter that you don't necessarily need to name. If anybody's going on to 130, eventually y'all will be naming these, so just be aware of that, but this is not one that I would require you to know. We've only done covalent nomenclature with 2 atoms in a compound, right? Does everybody see how that's trigonal planar?
So I thought that it couldn't have lone pairs.
Carbon does not.
Oh, the central atom.
Central atom, right?
Got it.
Yeah. Great question. So here, we're not looking at the geometry of oxygen here. If we were, what would the geometry of oxygen be?
Linear?
Linear, right? Does it make sense why? It's only attached to one other atom. Remember, the only thing you can do with 2 atoms attached together is attach them with a line. Okay? Does that make sense? Same would be true if we were looking at the hydrogens over here, right? Do you get what I'm saying about this idea of a central atom being kind of a wonky idea? It's just weird, right? Because here we're dealing with a relatively small molecule. It makes sense that this is your central atom, right? But that's not intuitive necessarily, right? That's why I like to go through that.
Professor?
Yes.
So when we're talking about doing geometry, are we only ever looking at the central atom and not the whole, like all of the atoms together?
So Sadie, I think you're in a lab that's already done part B.
Yeah.
Yeah. So what you do in part B is expand this concept of central atoms to large molecules, right? Where you could look at any of the atoms in the molecule and talk about their geometry, right? So
Okay.
the answer to your question is no, it doesn't have to be the central atom, but when you're doing molecules that only have one central atom, right, then it's kind of assumed that you understand that's the geometry that we're talking about. Does that make sense?
Yeah, that does.
Cool.
Thank you.
Yeah. That is definitely a confusing point that that books and a lot of the tutorials don't really go through. So, any other questions about trigonal planar? So, what I meant when I was talking about the 2-dimensional geometry, so I'm talking about planar. Planar is always going to be something that's in a plane, it's flat, right? So that geometry is flat. Linear, a line, also flat, right? It's just 2 points connected with a line. when we get into 4 attached atoms, that's when we get into a 3-dimensional geometry. And that's when they get a little bit harder to see, but we'll talk about how to see those. Everybody comfortable with 3 attached atoms, no lone pairs? Cool. So, next up, we want to talk about 3 total attachments, but now we're talking about 2 attached atoms and 1 lone pair. Okay? So here's what this looks like. So we have this same trigonal planar structure that we're starting off with, only instead of having an attached atom up here, we have a lone pair. Okay? Now, a lot of the times, the way that the tables draw this, they literally will draw it like this. I think it's a little confusing like that, because that's not the way it looks in the Lewis structure, right? It's not like coming off of the atom. So I like to draw it like this, okay? You guys all right with that? Cool. So in an example of a molecule that is, oh, I'm sorry, what is this geometry? Anybody know what this geometry is called?
Bent.
Bent. Right? So in the same way that 3 total attachments, where it was 3 attached atoms, had these 120-degree angles here, right? The 2 attached atoms and 1 lone pair, bent, has the same angles, right? And that's because this 120-degree angle is approximately what's necessary to keep the electrons maximum distance away from each other. Everybody still all right with me? Cool. So I think if you've drawn this structure 3-dimensionally, it's easy to see that it's bent, right? But if you drew it like this, which is probably your instinct, it's a lot harder to see that it's bent and not linear. Does that make sense? So do you have to draw things 3-dimensionally? No, but I think it really helps. Does that make sense, guys? Okay, so an example of this would be sulfur dioxide. Okay. Sulfur dioxide.
And just to clarify, this is determined because of the lone pair on the central atom.
Correct. Yes. So we're looking at the geometry of the sulfur atom, right? Now technically, now that we understand the octet rule and the fact that sulfur is able to exceed the octet rule, this is the best structure. But it doesn't change the fact that the geometry is still bent, okay? So this is another point that I think is really confusing for students. When we're talking about the geometry around the central atom here, we're talking about attached atoms, not the number of bonds, okay? Does that make sense? So here we have 2 attached atoms and 1 lone pair, right? It doesn't matter that these atoms are attached with double bonds, single bonds, triple bonds, any of that, right? Does that make sense, guys? So whether or not these are attached with single, double, or triple bonds does not matter. All we care about is how many attached atoms there are and how many lone pairs there are on that central atom, right? questions about this? We're okay? Cool. So if you had, so is there a possible arrangement of these where you could have one attached atom and two lone pairs? What shape is that?
Linear.
It's linear, right? So again, when you're talking about the structures, when you get down to having just an atom attached to another atom, it's always going to be linear, right? Does that make sense? So, so when we're talking about the geometry, we're really looking at the shape of the molecule, right, in 3 dimensions, or in 2 dimensions as it were here. So there are some cases where we just don't really need to think about it, right? So there is no trigonal planar molecule if you only have 2 attached atoms. Does that make sense, guys? Or if you only have 2 atoms attached to each other. So now we got to get up to 4 attachments. 4 total attachments. So if I have 4 total attachments and I have 4 attached atoms, okay, that is going to look like these. So this is a wedge I'm drawing, which is supposed to be representing this thing kind of coming out of the board, right? Kind of coming out at you. And then these dashes represent going back into the board. Okay. So this geometry is called tetrahedral. Tetrahedral. Everybody comfortable with the wedges and the dashes and how they're supposed to represent this thing in 3 dimensions? Do you get what I was saying before about what the other 2 were 3-dimensional geometry, or 2-dimensional geometries, and this one is the first 3-dimensional geometry that we've looked at? Cool.
Can you just go over what the dashes and the wedges represent?
Yeah, so the dashes are indicating that the atom is going back into the board, right? Going back in. And the wedge is saying it's coming out.
Okay, thank you.
Yeah. Let's see if I can... Now I wish I had brought my model kit home with me.
Professor?
Yeah.
Do we have to draw the dashes and the wedges, or just like present at the line in the homework, or do we have to draw like that?
Is that helpful? That's what we're talking about. I'm sorry. I'm gonna come back to you, Malin. But can you guys kind of see that? Right? 3-dimensional structure. It's not beautiful. So sorry. The question was, do I have to draw them 3-dimensionally? And the answer is no, because again, I'm not going to be asking you to actually draw structures on the quizzes or the tests. But I think it's a lot easier if you're drawing them 3-dimensionally to see the geometry, right? Does that make sense? So are you going to intuitively draw your structure this way the first time? Probably not. You'll probably have to put the structure together and then realize, oh, that's tetrahedral, and then draw it 3-dimensionally. Does that make sense? Kind of, sort of. So you guys...
I'm guessing we're going to go over how we know, like, that it's going to be 3-dimensional.
Well, okay, so there Okay, so the other possibility with this that we didn't talk about, but we can, is, right? Sorry, pretend like that's nice looking. There we go, right? Having 4 attached atoms that are in a plane, right? But is this going to maximize the distance between the electrons? So these are 90-degree angles, right? In 2 dimensions, this does maximize the angles, right? But it doesn't in 3 dimensions, and we know that molecules exist in 3 dimensions. So in 3 dimensions, the angles can be increased, right, by having the 3-dimensional shape instead of that 2-dimensional shape. Does that make sense? So why some are 3-dimensional and why some are 2-dimensional really has to do with the possible arrangements, right? So when you have a central atom that has 4 attached atoms, or some attached atoms and lone pairs, right, that total to 4, the bond angle that maximizes this distance is 109.5, right? Which is a bigger angle than 90 degrees, which is all you could get if you had this shape. Does that make sense? Did I answer your question, Jessie? Okay, cool. Let's see, there's a question in the chat. Yes, this will definitely be on the quiz next week. Cool. Questions about that? So this is no. It's yucky, right? This is yes. We like it.
So how would we draw like the wedge for like a double bond?
Same way, right? So this is kind of one of those weird areas where there's not a whole lot of molecules where you have to draw a double bond and have it be 3-dimensional. But we could look at an example of that if you guys want. Let's do... no. Sorry, I'm doing this wrong. I'm trying to think of an example that has that. No. I don't think that you have any molecules that are going to have more than 2 double bonds around a central atom and have 4 attached atoms. Does that make sense? So, like, the molecule that I was going to draw was phosphate, but phosphate is still only going to have it's still going to look like that, right? So I'm trying to, I can't come up off the top of my head. I can't think of an example where you would have 4 attached atoms and more than 2 double bonds around. It might exist, but it would be, if I can't come up with an example, it means you're probably not going to come across it, right? So, yeah.
Thank you.
Beep-boop. Not necessarily, Jessie, but you should be able to draw any of the chemical names that are given, right? So, will that come up as a question? Like, here's a chemical formula, what's the geometry? Yeah, that could happen, right? But usually, instead of giving chemical names, I would give you the structure. and say, what's this geometry? Does that make sense? So it's much more common for me to give you something like, let's say, that, and say, what's the geometry there, right? And you would say
Tetrahedral.
tetrahedral. Does that make sense, guys? Cool. Questions about tetrahedral? You guys all right with that one? Cool. All right. So now we're going to get into 3 attached atoms with 1 lone pair. So the way that we draw this guy, we take off 1 atom, we stick a lone pair on it, right? Now, why did I take off that atom specifically and not a different atom? The reason for that is because it makes the shape a lot easier to see, okay? So the geometry of something that has 3 attached atoms and 1 lone pair is called trigonal bipyramidal. Oof, sorry guys. Trigonal bipyramidal. Trigonal bipyramidal, they're pronounced either way. Students always get mad at me for pronouncing it pyramidal. I'm like, it just makes sense to me in my head, but they're like, pyramidal. Sure, whatever. Potato, potato. So, trigonal, I'm sorry, not bipyramidal, pyramidal. I'm sorry, you guys. This is my pregnancy brain. Pyramidal. Sorry, guys. This is the only way that it makes sense to me phonetically. Pyramidal. I just had a really stupid moment there for a second. Sorry. I was like, pyramid? Do you guys have those moments when you're studying chemistry that you're like, that shape? Yeah. Anyways, sorry. So, why trigonal pyramidal, or why trigonal pyramidal? Because what you essentially have, right, is a pyramid with 3 sides, right? A triangular pyramid. Does that make sense, guys? I know my drawing is not great, but can you see that, hopefully? Everybody all right with me?
Yes.
Cool. So, example of a molecule, whoops. That has a trigonal pyramidal structure would be this guy, NH3, aka ammonia. What would the covalent name for that guy be?
Nitrogen trihydride.
Nitrogen trihydride, right? But that's one of the common names that I would like you guys to know. Not because I'm going to test you on it, but just because it comes up so frequently in lab. And everybody sees how we have 1 lone pair and 3 attached atoms here. Questions? We're all right. Okay. May I erase? We're okay? Yeah? Okay. So, next up, we will have 2 attached atoms and 2 lone pairs. Okay. So here again, the central atom has 2 attached atoms, 2 lone pairs. This geometry is called bent. An example of a bent molecule would be water.
And would this still be 4 total attachments?
Mm-hmm.
Okay.
Yep.
Because
attached atoms plus lone pairs.
Okay.
Yeah. Mm-hmm. So when we're talking about total attachments, we're talking about the sum of attached atoms and lone pairs. Right? And so even though there's only 2 attached atoms in this molecule, we still have angles of 4 total attachments, right? Because we still are trying to maximize the distance between the lone pairs and the attached atoms, right? And the way that we do that is by having these 109.5 degree angles, right? They're not exactly that in these examples with lone pairs, but they're pretty close, okay? Does that make sense? Is everybody comfortable with why this is not linear? I think this is one of the most confusing ones for students.
Is
right?
this type of bent different than the type of bent that has 1 lone pair?
They're both the same idea. The angles are different, right? But in terms of what you guys should know for the shapes, usually if you can draw the shape, right, then you can figure out what the geometry is just by looking at it. Does that make sense? So specifically what we're talking about here is the geometry of the molecule, right? So the molecule geometry is determined by the total number of attachments. There's also a thing called the electron geometry, which you guys might have seen in some of the lectures with other like YouTube people. And I'm not going to ask you guys to know the electron geometry, but if you have 4 total attachments, then the electron geometry would be tetrahedral, right? And that's what determines the angle of this bent as being 109.5 versus the trigonal planar bent, which is about 120. Sorry, I went off the map there.
Are you going to ever ask us for those exact numbers?
No. Mm-mm. No, I don't care if you remember the bond angles. I think it's enough to be getting on with to recognize the shapes, right? But I think it's helpful. I think the angles can be helpful if you're somebody who's been doing trig or something like that, you know what I mean? Or if your brain just works better. Some people just, their brains work better like 3-dimensionally, like shape-wise than mine do. My brain is terrible at doing this, right? So it's really hard for me to see this kind of stuff, these angles and things like that. There are simulations and 3D molecular models that you guys can go online and play with. So if you guys just look up molecule simulations, you'll see there's tons of these that have like three-dimensional molecules. You can like move them around and like change the angles and see what happens. So there's a lot of that out there. If you have a hard time visualizing this, which I do, that can be helpful. There's also modeling kits, which are basically just fancy ball and stick models that can help you represent these molecules three-dimensionally. A lot of students find those helpful. I personally was too lazy to ever really get with the molecule building kits, so I probably shouldn't admit that on the line, but whatever. But yeah, I hated modeling kits. I was like, what am I, an engineer? I don't want to put this together. So yeah, but basically, long story short, what you need to be able to do with this information is identify the molecular geometry, meaning the shape of the molecule, right? So that would be bent, trigonal, pyramidal, tetrahedral, trigonal planar, or linear, right? So there's not too many here. I'll write all those down. May I erase? Yeah, we cool. So if we have two attached atoms, that's going to be linear. Three attached atoms, trigonal planar. Two attached atoms, one lone pair. It's going to be bent. Four attached atoms. Whoops. Is going to be tetrahedral. Tetrahedral. There we go. Tetrahedral. Three attached atoms and one lone pair will be trigonal pyramidal. And two attached atoms with two lone pairs is bent. Right? Those are your guys. Everybody alright with me on that?
Do you mind moving up the board just a little? I can't see the last one. Thank you.
Uh-huh. Any other questions about those? Everybody's all right? May I erase? Cool. All right. So, that's geometry. Now we're going to talk about polarity. Okay. Polarity is basically unequal sharing. Oops. Of electrons. Okay. So we talked about covalent bonds as being a shared electron bond, right? But that sharing doesn't always have to be equitable sharing, right? So we can have, we can have polar covalent bonds, which share electrons unequally. or you can have nonpolar covalent bonds. These guys share equally. Right? So, why are electrons shared unequally? That has to do with electronegativity. Okay. So, some atoms want electrons more than other atoms, right? That quality of wanting more electrons, that electron greediness, that's electronegativity. Right? Who's the most electronegative element on the periodic table?
Fluorine.
Fluorine, right? As you go down and diagonally away from fluorine, you become less and less electronegative, right? So when we talk about electronegativity, what we're really talking about in a bond is the difference in electronegativity. So, for example, if we have this guy, HF, we know that fluorine is super electronegative, right? Hydrogen, relatively speaking, not very electronegative, right? So, because this guy wants to hog electrons, right? It's electron greedy. It means that we're going to get extra electrons on this side, which means we will have less electrons on this side. That is a polar bond. So, another way that we talk about this is in terms of what is known as a dipole, which is just a fancy way of saying, which is just a fancy way of saying we have partial charges on the molecule or on the bond. Okay? So, I was talking about electrons here, and now I'm talking about charges, right? Why are those the same thing? Why is it okay for me to be talking about electrons here, extra electrons or less electrons, and then talking about charges down here?
Because that's what a charge is.
Yeah, the charges in this case come from the electrons. Does that make sense? So, we're not talking about here formal charges. Not formal charges, okay? Partial charges, okay? So, who's going to have a partial negative charge in this molecule?
Fluorine.
Fluorine, right? Because it's got extra electrons. Electrons are negative, right? So if it's hogging more of the electrons, then that means that there will be a partial negative on fluorine, right? This little weird D is the baby delta and a negative sign. That's how we indicate that there is a partial negative charge on fluorine.
Are you saying dipoles are not formal charges?
Not formal.
Okay, thank you.
Yeah. So what does that mean, the partial charges on hydrogen over here?
Positive.
Partial positive. Okay. The way that we draw the dipole in is as an arrow pointing toward where the electrons are most, with a little positive end on the tail here. So this is how we represent a dipole. Okay? So there's multiple representations here, multiple ways that we talk about this. Depending on the size of the molecule, one might be easier to represent than another. But we'll talk about the dipoles in 3 dimensions when we start talking about molecular polarity, right? Having the dipoles in 3 dimensions will matter. So at this point, what we're talking about is just polar bonds, right? We're talking about polar covalent bonds, and how to understand where the charges are based on electronegativity. Does that make sense, guys? Cool. We said there's also nonpolar covalent bonds, right? That would be somebody that's sharing equally with a partner. Now, I think it's much easier to remember who is nonpolar covalent than who is polar covalent, because most combinations of atoms are, at least to some degree, going to be polar covalent. All right? May I erase? Cool. So let's talk about who will always be nonpolar for our purposes. Anything bonded to itself. So examples of this would be diatomics. Right? It's not the only example, but it's a common example. Anything bonded to itself, and anything with carbon and hydrogen bonded together, right? Carbon and hydrogen are very close together in electronegativity, so they will always form non-polar bonds. Okay? So, again, I think it's much easier to think about polarity in terms of who doesn't make polar bonds than it is who does make polar bonds. Does that make sense? Cool. So these you should have memorized. Cool. Okay. Everybody still with me?
So then, what would be the difference between a formal charge versus...
I was just going to talk about that. You took the words right out of my mouth. So we have polar covalent bonds, right? We have non-polar covalent bonds. And then we have ionic bonds, right? So when we talk about bonds, we have this kind of spectrum of sharing that we use, right? Where nonpolar covalent would be the nicest, most equitable sharing, right? Polar covalent would be somewhat less equitable sharing, so that you end up with these kind of partial charges. And ionic bonding, which ends up having a complete exchange of electrons, right? So basically, you're not sharing, you're taking from another atom. Does that make sense? So if there are formal charges on a molecule, then you're not going to be talking about the polarity of the molecule. Okay? So is it okay if I erase, guys? Cool. So that brings us to the next thing we want to talk about. So we talked about polar bonds. Now we want to talk about polar molecules. Right? So a polar molecule means that the overall molecule has a net dipole. Okay? What the heck does that mean? And this is as opposed to an ion, right? So you can have an ion, you can have a polar molecule. A polar molecule has partial charges, right? But an ion has formal charges. Okay? And we've already talked about that at length. Okay? So if you have a formal charge, you're dealing with an ion. If you do not have a formal charge, then you're probably dealing with either a polar molecule or a non-polar molecule. Okay? Yes, Jessie?
In the examples where you first evaluate the octet rule and then you draw the little square around the atom to see if its charge is positive or negative, what is that called? Is that called a partial charge, or?
That's evaluating for formal charges.
That's a formal charge.
Yes, those are formal charges. Yeah.
Do you always write that on the, like, draw that out if there is one? You always signify that?
Mm-hmm. Yes. Yeah. So basically, one of the things that's extremely predictive of molecular behavior is how the electrons are distributed, right? So if you have formal charges, then it means that you're going to have a molecule that's behaving like an ion, right? There's going to be positive ends attracted to negative ends, right? That's how they'll assemble. When you're talking about polar molecules, you have partial charges, but those partial charges are still strong enough to give rise to things like a liquid or a solid phase, right? So if all molecules were nonpolar, then all molecules would be gases, right? Human beings, plants, things like that would not exist, right? So all of these, quote, condensed phases, liquids and solids, are formed by these polar interactions, right? Or ionic interactions. So this is not trivial in terms of understanding how molecules behave. Does that make sense? Cool. So they're all really good questions, you guys. Thank you. Okay, so in order to be a polar molecule, so we kind of defined it in these hard to understand terms. So now let's define it in something that's a little bit more straightforward. So in order to have a polar molecule, the molecule must have polar bonds. right? So if you have a molecule that doesn't have any polar bonds, then there's no way it can be a polar molecule. Does that make sense? Examples of that would be, let's do, I want to confuse you, nonpolar. Oops, you guys can't see that. Nonpolar molecule would be sorry, it's bad. This guy. It's carbon attached to a bunch of hydrogens. Why is that nonpolar?
Because carbon and hydrogen bonds will always be nonpolar.
Exactly, right? So if the only thing I have here are carbon attached to a bunch of hydrogens, that will be nonpolar. Everybody all right with that? Cool. So first thing we have to have is polar bonds. The next thing we have to have is asymmetry. Symmetry. Let me try that again. Huh? You guys, I have no idea how to spell. This word in particular just ruins my life. Asymmetry. It's not asymmetry, I'm pretty sure. I don't know. Sim. Oh my god, you guys, sorry. My partner and I always make fun of each other. We're like, dude, people pay us to teach them. We're idiots. Don't tell my boss I said that. This will be on the internet for the rest of my life. Okay, so asymmetry. What the heck does that mean? So when we talk about our geometries, any of the geometries without lone pairs are symmetric. Geometries with lone pairs are asymmetric. Oh my god, you guys, I really can't spell this word. Asymmetric. Okay? So, can I erase this so that I can do another summary table? Cool. So, in order to have a nonpolar molecule, I'm sorry, a polar molecule, oops, sorry. Just to hope my phone doesn't die. So in order to have a polar molecule, you must have a geometry with lone pairs. So that would be bent, right? Either one of them. Trigonal, pyramidal, right? Those are your main geometries without lone pairs, okay? Nonpolar will be, oops, linear, trigonal planar, and tetrahedral. Okay, now this is assuming you have the same attached atoms. Around your central molecule. Central atom. Okay, so for example, we had this guy. Right? And we said that guy is nonpolar, right? Now that's nonpolar because all of the attached atoms are the same attached atom, and all of them have nonpolar bonds, right? But you don't have to have all the same attached atoms, right? If I took one of these guys and replaced it with something like that, right? Now, this is a polar molecule because having this different attached atom gives the molecule asymmetry. Okay? So, three things that can make a molecule, or two things really, that can make a molecule polar, right? You can have, so first of all, you have to have polar bonds, right? So that's just kind of a baseline. If you don't have polar bonds, you can't have a polar molecule. And then an asymmetry of some kind, right? So that asymmetry can either be an asymmetric geometry, right? Or it can be asymmetric attached atoms, okay? Meaning you don't have all of the same attached atoms around. Everybody all right with me there? I'm going to turn this off so it doesn't die.